All right, so I am resuming this video. Where was I? So I'd gotten through number 17. Let's look at number 32. In number 32, it's asking where various functions are continuous. And the thing you want to keep in mind is any sort of reasonable function with a formula that's not piecewise is continuous wherever it's defined. So for 32a, the function was f of x is x over absolute value of x minus 3. So the only thing that could go wrong here is division by 0. So we need that the absolute value of x minus 3 is not 0, which means the absolute value of x is not 3, which means x is not 3 or negative 1. So essentially this function is continuous except at those places. So if you want it to be really fancy, you could say it's continuous on the interval from negative infinity to negative 3, and then on the interval from negative 3 to 3, and then on the interval from 3 to infinity. I'm not really too concerned with exactly how you say this, as long as you understand that discontinuities occur at negative 3 and 3. For C, we have f of x is e to the natural log of x power. There's a little bit of a trick here. You probably want to say that that's equal to x, and it is equal to x where it's defined. But if we take this literally, we need to think what could go wrong here. We need natural log of x to exist in the first place, and that only happens when x is greater than 0. So that's where this function is defined, and that's where it's continuous. If you were to graph it on your calculator, literally typed in like that, it would look like y equals x, but it would start at the origin. So that's just a little trick. Okay, 33. So for 33, we are given that f of x is negative x to the 4th plus 3 for x less than or equal to 2, and x squared plus 9 for x is greater than 2. And we want to know, is it continuous everywhere? So I'm actually going to explain this, right? It says justify your conclusion. That's an expression on the AP a lot, justify your answer, right? We want to use sentences. So we know these individual formulas are polynomials which are continuous. So as long as this part is followed for x smaller than 2, or this part followed for x equal to 2, there are no problems. So we could say something like, the individual formulas are polynomials and therefore continuous, so f is continuous for x smaller than 2 and x greater than 2. Because these pieces are nice continuous functions. But when we see a piecewise defined function, it's certainly possible that I have, nice continuous function, and then out of nowhere I jump discontinuity to another nice continuous function. We now need to think about what's happening at x equals 2, and we really want to use the language of limits to express that. So let's think about the limit as x approaches 2 from the negative side. If x is a little bit smaller than 2, then the relevant formula is this one. And I love to just plug in. If I do that there, I get, plug in 2, I get negative 16 plus 3, which is negative 13. From the positive side, if x is a little bit bigger than 2, my function is x squared plus 9. Love to plug in, I get 13. And these are not the same, right? They're almost the same. This problem maybe was cooked up to make you go carefully. Maybe it was actually an error and they wanted them to be the same, but they're not. One of them is negative 13 and one of them is positive 13. So what we could observe here is that the limit as x approaches 2 of f of x does not exist. And that's required for being continuous. So f is discontinuous at x equals 2. If these happen to be equal to each other, then the limit does exist, and it would be equal to the value, so you would have continuity. But what you need to do in problems like this is very carefully just say, what is the limit from the left? Use correct notation to express that. What is the limit from the right? Use correct notation to express that. And then just observe if they're the same. So this is not continuous everywhere. And any more from this? Number 37 is the last from the book. Show that the equation x to the fourth plus 5x to the third plus 5x minus 1 equals 0 has at least 2 real solutions. In the interval from -6 to 2. So there's a little bit of a trick here with 2 of them. So I'm going to do some just playing around and then erase it. And this is what you will need to do. Right? Math is not, so, this is like writing an essay. Sometimes you just have to do a first draft and then fix it. I am going to figure some stuff out and then decide what I need to keep. What you should not have as your attitude, this is just practice, but if this were graded homework, your attitude should be, I'm not going to present everything I did, I'm going to present what ultimately is part of my solution. So let's just try plugging in really easy things, and let's give this thing a name, right? So I'll call this f of x, and this is me playing around. I'm going to fix it later on. So that's f of x. F of 0 is really easy to plug in, that's -1. F of 1, if I plug that in, that's pretty easy. That's 1 plus 5 plus 5 minus 1, which is 10. Trying to figure out when it's 0, already I have a negative and a positive. Problems like this probably use the intermediate value theorem. Let's see if I plug in a negative. F of -1 would be 1 minus 5 plus 5 minus 1 is equal to 0. That's not helpful. Let's try f of -2. F of -2 would be 16 minus 40 minus 10. Oh, wait, actually, finding the 0 is actually super helpful. Okay, so let's all right, so here's what we can do. So I just need -1, 0, and 1. Oh, did I do this wrong? Sorry, okay. Right, this is not, I'm just talking through this. Let's do this more carefully. F of 0 is definitely -1. F of 1 is 1 plus 5 plus 5 minus 1, which is 10. F of -1, I think I goofed on that. F of -1 is 1 minus 5 minus 5 minus 1, which is -10. What is, say, f of, maybe let's just do -6. I promise you I won't make you play around with all this guess and check on an actual test problem when the clock is ticking. So if I plug in -6, that's that to the -6 to the 4th power is 1296. And then that would be minus 5 times 216, which would be -580. No, -1080, sorry. Doing this without a calculator. I apologize. I didn't realize it was saying we had to find 2 of them. Just pay attention to the real gist of this, and you'll be okay. Minus 30 minus 1, which is 216 minus 31, which is 185. Let's just assume that's correct. All right, so all of this is just scratch work. Now let me give my real statement. So f of negative 6 is 185, and f of 0 is negative 1. So what we're observing here is we had a positive value and then a negative value later on. So let me take this back. I really want to, so I'm going to write exactly what you should write in terms of an explanation. So let f of x equal x to the fourth plus 5x squared plus 5x minus 1. That function notation did not exist in the problem, so we're introducing it. And then I'm just asserting that f of negative 6 is 185, f of 0 is negative 1. We don't need to explain where that came from. It was in our scratch work. But the key is f had a positive value and then later on had a negative value, so we know it must have been 0 somewhere in between. F is continuous because it's a polynomial. And we observe, and just make this clear, so since 0 is between f of negative 6, our starting y value, and f of 0, our ending y value, by the intermediate value theorem, there must be some x1, and you'll see why I call it x1 in a second, between negative 6 and 0, such that f of x1 is equal to 0. I have a continuous function. It used to have a positive value, and later on it had a negative value. It must have had a value of 0 somewhere in between. Now, f of 0 is negative 1, but f of 1 is 10. So what happens is if I keep going, it switches from negative back to positive. So there's at least two switches. It was positive, then later on negative, then positive again. It must have switched again. So now we can say, if we apply the intermediate value theorem again, it's the same function, so it's still continuous. 0 is still between these two values. There must be some x2 between 0 and 1, right? Between these two x values, with f of x2 equals 0. And the key is these are different. x1 happened between negative 6 and 0. The second one happened between 0 and 1. Right, just in terms of a little picture. This picture is not part of your argument, but it helps you understand. When x is negative 6, we were down here. We had a positive value. When x was 0, we had a negative value. When x was 1, we had a positive value. So the idea is this continuous function, it crossed the x-axis once over here and then once again over here. So you can now say something like, we have observed that there are two values in the interval from negative 6 to 2 that satisfy the original equation. I wouldn't ask you to explain why there are two, and I certainly wouldn't force you to muck around with all of that arithmetic, but you need to understand this principle. If I have a continuous function that's positive in one place and negative in another, it must be 0 in between. And it's not even about 0. If I have a continuous function that's above 4 in one place and below 4 in another place, it must be equal to y equals 4 somewhere in between. The number doesn't matter. All right, let me stop this video again.